So let's look at some properties of matter. Why the properties are important? Because we want to look at compounds. And remember that compounds are formed from a combination of two or more elements. So what is it that makes compounds to react with each other? What is it that makes them form a new compound? So that's the chemical changes or chemical properties, and also physical properties are important. Those are the properties of the element. So chemical properties would tell us how each compound would react, does chemical reactions, and then physical properties give some physical property information like the density, melting point, boiling point, that these are all important to us. So we're gonna start this chapter by look at properties of the matter, which are chemical and physical properties. We look at the chemical and physical changes, and then we look at a type of energy in the form of a heat that's associated with any chemical process. We choose heat to start off with because almost every single process that we do involves some sort of transfer of heat. We look at the flow of the heat and also the quantity of heat that's involved when a chemical process is done. Now, as I said, each substance has a set of properties, and those properties are characteristic of every substance. So the properties that we look at are physical and chemical properties. So physical properties of any substance, any matter, can be determined without altering the composition of that substance. So some examples of physical properties are like color, odor, taste, shape, like the physical states, density, melting point, and boiling point. Chemical properties, on the other hand, those explain the ability of a substance to go through a change. And when that change happens, the composition of the substance is going to change. So for example, if water molecule decomposes, so the decomposition of water is a chemical property of water. And when it decomposes, it forms hydrogen and oxygen gas. It's not water anymore. So the composition of our substance, which is water, has changed. Now, we also look at chemical changes and physical changes in chemistry. So chemical change is when the composition of matter changes. For example, here you see the reaction of sodium metal and chlorine gas. Sodium metal by itself, before it does any reaction, it's a metal. It's shiny, it's solid. Chlorine, on the other hand, is a gas, and it's yellow. Now, when sodium and chlorine react with each other, they form sodium chloride. Now, sodium chloride is completely different from chlorine and sodium. The physical and chemical properties of sodium chloride is completely different from sodium and chlorine. Now, sodium chloride is a white powder. Sodium chloride is not toxic anymore, whereas sodium metal or chlorine gas by themselves, they're toxic. So sodium and chlorine react with each other, undergo a chemical change, and from that chemical change, sodium chloride is formed, which has a different chemical and physical properties than what it's made of, which are sodium and chlorine. So physical properties of substances are different. So we don't have any two substances that have the exact same type of physical properties or chemical properties. They may be physical and chemical properties that are common in between them, but there is always one property that's different, which it can distinguish that substance from another one. Therefore, these physical and chemical properties, we can use them as a method to identify our unknown substances. For example, density. Density is a physical properties. We talked about this before. You know, you can measure the density of any unknown in a chemical lab, and knowing that, you know, if you end up with, you know, 1 gram per milliliter at 4 degrees Celsius, there is a good possibility that your unknown liquid could be water. But is density enough to say, you know, your liquid is water? No, we want to pay attention to other things too. You know, it has to be clear, it has to be colorless, it has to be odorless. There are other things that are important too. But with physical properties, you know, you can narrow down your search and do more testing, more experiments to identify exactly what compounds you have. So chemical changes, the composition of the matter alters. Whereas when you look at the physical changes, it's mainly the change in the state of the matter, and the composition does not change. For example, on this picture here, you know, cutting wood. When you cut it, the composition doesn't change. It's still wood. It's just, you know, smaller pieces. Or when something evaporates, let's say you boil water, you know, you have a steam and you have liquid water. They're both water. It's just that the physical state, you're going from liquid to the gas, but you still have water. It's still H2O, just the physical state is different. And again, whereas when you have a chemical change, the composition of the matter changes. The picture here shows a chemical change that copper metal goes through. So copper metal by itself, it's a shiny metal and it has that characteristic copperic color to it. When it reacts with oxygen, which is the clear colorless gas, it forms copper oxide. Now copper oxide is, you can call it a rust. It's a metal oxide and it has a black color. Now copper oxide is a different compound than copper and oxygen. Physical and chemical properties of copper oxide is totally different from copper metal and oxygen gas. So again, chemical change is when the composition of matter alters, but physical change is when the composition of the matter or the composition of the substance is not altered during a process. So let's look at an example. Which of the following is a physical change? Do you think grinding a rock into powder, is that a physical or a chemical change? Physical change, very good. Because you're just grinding, you're not changing the composition of the rock. Hydrogen and oxygen reacting to form water, is that physical or chemical change? Chemical change, very good. Because they react, they change, they form a new compound, which is water. So a shovel rusting, is that chemical or physical change? It's a chemical change. Rusting is the combination or the reaction of any metal with the oxygen, and it forms metal oxide, so it goes through a change. And acid and base react to form water. That's a chemical change too. Just the word react tells you that basically a reaction is happening. It's a chemical change. Burning sugar, this is also a chemical change, because when you burn sugar, have you seen it? When you burn it, it becomes black. So it actually decomposes. So that's also a chemical change. So the only physical change here is grinding a rock into powder. Let's look at another example. Which of the following is a chemical change? Melting aspirin, do you think that's a physical or chemical change? It's physical. Any melting, boiling, evaporating, freezing, those are all physical, because the only thing that's changing is the physical state. So aspirin, when it's melted, it goes from a solid aspirin to liquid aspirin. It's not decomposing, it's not turning into anything else, it's just melting. So that's a physical change. Breaking a plate, that's a physical change too, because when you break a plate, you just break it into smaller pieces. The composition doesn't change. Boiling antifreeze, This is also physical because we're just boiling it off. When you boil, you're basically making the forces in between the antifreeze molecules weaker, so it boils off. Putting sugar in tea, physical or chemical? It is also a physical change because when you put sugar in tea, you're just dissolving sugar in the tea, but sugar stays as sugar, you know. It's still sweet and it's sugar. Lighting a match, it's a chemical change because when you light a match, any burning is the reaction with oxygen. So basically the match is burning, and after it's burned, you don't have the match anymore, you know, it's not usable. So lighting a match is a chemical change. Questions? So in order to show chemical reactions or equation or changes, we show the reaction in terms of an equation. So we use the formula of compounds and we show how the change is occurred. We show what we start off with and what substances we end up with. For example, let's look at the reaction of decomposition of water. So H2O, which is a liquid, if we heat it up, it decomposes into hydrogen gas and oxygen gas. So the coefficients I put here is for balancing the reaction. We'll talk about them and we will actually learn how to come up with this. So this equation represents a decomposition of water. So when I look at this, I can tell that if you have liquid water and decompose it, it will decompose into hydrogen gas and oxygen gas. So a couple of things that are important in terms of reading the chemical equations is looking at, first of all, the arrow. This arrow tells you the direction of the reaction and it's always pointing towards the product. So this arrow points towards hydrogen and oxygen gas. So I can tell now that my products are hydrogen and oxygen and the reactant is water. So by just looking at the arrow, I know that I'm looking at decomposition of water. H2O liquid gives you hydrogen and oxygen gas. Now, another information, lots of information we can get from chemical equations. Another information is the physical state of every single reactant and product here. So when I look at this reaction, I know that, you know, the decomposition was done on liquid water. And what I got was hydrogen gas and oxygen gas. So in chemical equations, you would always see the physical state of every single reactant and product. Now, sometimes the conditions in which reactions are done will be mentioned in a chemical equation. For example, you can put a triangle here. The triangle in chemistry always represents heat. If it's a symbol, it represents heat. In equations and formulas, it represents change. So now I have more information here, meaning that in order to decompose water, heat is required. And if you apply heat, water is going to decompose into hydrogen and oxygen gas. The other information that you can get from chemical equations is these coefficients that come right before any chemical formula. We will learn later on that these represents the ratio in between the reactants and products. What does it mean? It means that if two water molecules decomposes, from that decomposition of two water molecules, you will get exactly 2 molecules of hydrogen and 1 molecule of oxygen. We will show you later that these coefficients are important for the law of conservation of mass. So during a chemical reaction, no mass can be produced or destroyed. So we're gonna need to have coefficients to balance our reactions, and we will learn that later on. Now that we know a little bit about chemical equations and chemical changes, let's look at the heat that's involved during a chemical reaction. I just showed you that sometimes in order to get a reaction going, we need to use heat. For example, for decomposition of, let's say, even sugar. You gotta heat it up to decompose the sugar. Now, sometimes from chemical reactions, heat is produced. So it is important for us to know if heat is produced or used during a chemical reaction. And also, it's very important for us as scientists to know the quantity, the amount of heat that is either released or used during a chemical reaction. And why is this important? It is important because, in terms of planning your reaction, it's extremely important. Let's say I want to decompose the sugar. Can I just let it sit on this bench top to decompose? No. So I gotta do a little bit of research and realize that in order to decompose sugar, I need heat. So unless I heat up sugar, it's not going to decompose. But just any heat would work? No, the quantity of the heat is important too. I should know exactly how much heat to provide to decompose the sugar, for example. So this becomes extremely important when you do synthesis and when you do chemical reactions in a lab, because some reactions require some sort of heat to get going. And if you don't provide the heat, or if you don't provide the amount required, no reaction is going to take place. Oftentimes we do a chemical reaction and from the reaction heat is produced. So we got to be ready for it. If you're in a lab and you want to do a reaction in a very, very large quantity and you have no idea how much heat is going to be produced, that's dangerous. It could explode and it could cause problems. So heat is a type of energy that's always involved in chemical reactions. So our focus here is to look at the heat, the flow, see if heat is absorbed or gained during a chemical reaction. And we also want to know the quantity of the heat, how much heat is absorbed or gained during a chemical reaction. Now, before we work on the direction of the flow of the heat or the quantity, we need to define a unit for heat. So the SI unit for heat in the metric system, the unit is joules. And joules is defined as the energy that's required to change the temperature of 1 gram of water by 1 degree Celsius, and that amount is 4.184 joules. Now later on, this 4.184 joules, which is the energy required to change the temperature of 1 gram of water by 1 degree Celsius, we show you that's the specific heat of a substance. Now, the unit of heat that may be more familiar to you is calorie. So each calorie is 4.184 joules. But calorie is a very, very small unit. So when it gets to food, anything that we consume, the calories are usually given in kilocalorie. So kilo, remember that this stands for 1000, and the kilocalorie, we show it with a capital C. So if you see on a label that says 20 C calories, it means that it basically has 20 times 1,000 calories. But if it's just 20 cal, it's just basically 20 calories. So when you look at the calorie intake or in the problems, pay attention to that C, if it is uppercase C or a lowercase c. Now let's look at the difference between heat and temperature. So heat is energy. Temperature is a scale, is a measure that shows us the intensity of the heat. Now we want to look at, so we use temperature to show us how hot or how cold something is, processes, or how cold or how hot a substance is. Now let's look at a couple of reactions that involves heat. We're gonna first look at the energy, the units of energy, and then we're gonna show you how we can find the magnitude of the heat exactly. So the reaction that you see here is a reaction of methane. It's a combustion reaction. Methane is reacting with oxygen, and from that reaction, carbon dioxide and water is formed. And we know that from this reaction, 802.5 kilojoules of heat is formed. So what this means is that when methane reacts with oxygen, heat is released, right? Because heat appears as one of your products in this reaction. So you want to find the amount of energy that's produced during this combustion reaction. So to find the amount of energy in calories, you know that each calorie is 4.184 joules. And when we say kilojoules, that kilo stands for 1,000. Remember, kilo is a prefix and joule is your unit. So in order to do this conversion here, you want to go from kilojoules to joules first, and then from joules to calorie. And this would be the amount of heat that's released in calories. So on the back of the periodic tables that's provided to you, if you look at the, so first of all, on the back of this periodic table, there are some information that you can find. Use this when you study. And so the conversion in between calorie and joules is given on the back of the periodic table. So if you look at the third box from the top, you have the conversion between calorie and joules. You don't need to memorize it. It's here, but know that it's here for the test. Now, let's try to quantify the amount of heat. Quantize, basically. So in order to be able to find the magnitude of the heat, there are a couple of things, few things that are important. One of the important factors is the specific heat of a substance. So specific heat of a substance is defined as the amount of heat that's required to change the temperature of 1 gram of the material by 1 degree Celsius. So this basically tells you how much you should heat a substance in order to change the temperature of that substance. For example, if you look at this table water, the specific heat of water is 4.184 joules per gram Celsius. Meaning that, in order to change the temperature of 1 gram of water, you need to apply 4.184 joules of energy. And when you do that, the temperature of water is going to change 1 degree Celsius. Now, for example, if you look at aluminum, the specific heat of aluminum is only 0.9 compared to water. What does it mean? It means that in order to change the temperature of aluminum, you only need to provide 0.9 joules of heat per gram of aluminum. What this tells me is that it's a lot easier to change the temperature of aluminum than water. Aluminum is a metal. Remember that one of the physical properties of metals is that they're a conductor of heat. So all the metals have very, very low specific heat just because they're conductors. That's why we never use them as insulator, because let's say, I don't know, something catches on fire and you put aluminum to block it. No way. The heat can easily transfer because aluminum doesn't absorb that heat. When something is an insulator, the specific heat is going to be high, meaning that that substance is going to hold the heat without changing its temperature. Now, if you look at this table here, you see that the metals have a very low specific heat. Non-metals have a higher specific heat, and water exceptionally has a very high specific heat. Now, knowing a specific heat or specific heat capacity, let's look at a formula where we can find the quantity or magnitude of heat. So the heat depends on a couple of factors. First of all, Q is heat. So heat depends on the amount of substance. For example, let's say you're trying to boil 1 cup of water or a big pot of water. Which one requires more heat to boil? The big pot of water. So they're both water, same thing. The only thing that's different is the amount. So the heat depends on the mass of the substance. Now this C represents the specific heat. Meaning that the amount of heat required depends, or the amount of heat involved in a process depends on the type of the material, identity of your material. For example, if you have 2 grams of iron and 2 grams of water, the amount of heat that you're going to use to change their temperature, let's say by 1 degree Celsius, is not going to be the same. The mass is the same, the change in temperature is the same, but the identity is different. So iron has a lower heat capacity, water has a higher heat capacity. So you would need more heat in order to change the temperature of 2 grams of water compared to 2 grams of iron. Now delta T represents the change in temperature, meaning that how hot or how cold you're gonna get something. Now delta T is defined as T2 minus T1. T2 is the final temperature and T1 is the initial temperature. It's important for delta T to be T2 final minus initial, because I'm going to show you later on that the sign of delta T is important and it gives us information. So remember that whenever we're looking at a change, it's always final minus initial. Some textbook even show this as TF minus T initial, just T final minus T initial. So Q equals to MC delta T. This is the equation we use in order to find the quantity of the heat that's involved in a chemical reaction. Make sure you memorize this equation. Now, before we move on and do practice problems, let's look at the units. What is the unit of heat? What's the SI unit of heat? Joules, very good. Mass in this equation is in grams. Delta T is in degrees Celsius. Specific heat is joules per gram Celsius. So, unit of heat is joules. Mass is given in grams. Specific heat or heat capacity is joules per gram Celsius. And delta T is in degrees Celsius. Let's look at an example. How much heat is needed to raise the temperature of 20 grams of water by 10 degrees Celsius? So let's see what's given to us. How much heat is needed, meaning that we're solving for Q, to raise the temperature of 200 grams of water. So mass of water is 200 grams by 10 degrees Celsius, meaning that delta T is 10 degrees Celsius. Specific heat of water is 4.184 joules per gram Celsius. So we're solving for Q. We know that Q equals to MC delta T. Therefore, Q equals to M, which is 200 grams. Delta T, 4.184 joules per gram Celsius. And delta T is already given to us, which is 10 degrees Celsius. Use your calculators, please, and find the quantity of heat here. So how many significant figures do we want? Very good, 3 significant figures. So the answer is 8.37 times 10 to the 3 joules. Now, let's double check, see if everything makes sense or not. In terms of units, look, gram and gram cancel out, degree Celsius cancel out, you end up with joules. And we were solving for Q, so this is the correct unit. It tells us that we did, and we set up the equation, the formula properly. Now, when it gets to heat, remember I've been saying that heat can either be absorbed or released. So the quantity of heat, we can find it from Q equals to mc delta T. But how can we tell if heat was absorbed or released during a chemical process or chemical reaction? So in order to see if heat is absorbed or released during a chemical reaction, we look at the sign of the Q. So if Q is positive, it means that heat was absorbed during the chemical reaction. If Q is negative, it means that heat is released during the chemical reaction. Now, if Q is positive, or if heat absorbed is absorbed during a chemical reaction, we call that reaction an endothermic reaction. And if heat is absorbed during a chemical reaction, we call that an exothermic reaction. So we can have positive Q or negative Q. But positive or negative would tell us only if the reaction is exothermic or endothermic. It doesn't change the magnitude of the heat. It just tells us the flow of heat, if heat was absorbed or released during a chemical reaction. Now, the sign of Q depends on the sign of delta T. So if your delta T is positive, Q is going to be positive. If delta T is negative, Q is going to be negative. So it's important to identify final and initial temperature correctly, and make sure that when you do delta T, you always do final minus initial. Mass cannot be a negative number. Heat capacity cannot be a negative number. But delta T can be negative. And if delta T is negative, it means that final temperature is lower than the initial temperature. It means that heat, if final temperature is lower, yes, it means that heat is released and your Q becomes a negative number. So let's look at another example. You want to calculate the specific heat of an unknown if 1638 joules raises the temperature of 125 grams from 25 degrees Celsius to 52.6 degrees Celsius. So let's see what's given to us. You want to calculate the specific heat, so we're solving for C of an unknown. If 1638 joules, what does that represent, the 1638 joules? That's Q, very good, that's the heat, is 1638 joules. How do I know? By just looking at the unit. Raises the temperature of 125 grams, so mass is 125 grams. From 25 degrees Celsius, so T1 is 25 degrees Celsius, to T2, which is 52.6 degrees Celsius. So in order to find Q, in order anything that related to heat, Q equals to MC delta T. Now we're solving for C, we have to isolate C. In order to isolate C, we're going to divide both sides by M delta T. Now M delta T cancel out. Therefore, C is going to equal to Q over M delta T. Now we just have to plug in what's given to us. So C, Q is 1638 joules. Mass is 125 grams. Delta T is T2, 52.6, minus T1, 25 degrees Celsius. So use your calculator, please, and find C. So what's the answer? I have 0.475. And then in terms of unit, it comes out to joules per gram Celsius. So keep in mind that energy that's involved in a chemical reaction is not only in a form of heat. There are many different types of energies that are involved during a chemical reaction. The most important thing to know is that energy is conserved during a chemical reaction. No energy is produced nor destroyed. Energy can be transformed from one type to another type. Depending on what type of energy we use, we actually use the transformation of energy to get things going. So we learned properties of substances, physical and chemical changes, and also energy, the quantity of